Are there any questions? No? Do you guys remember the rules for drawing Lewis structures? Count the valence electrons, come up with some kind of skeleton structure. Complete the octets to the outer electrons first. If you have extra electrons, you leave the extra electrons in the middle. If you're short, then you make double bonds, multiple bonds. That's pretty much it in a nutshell. And so let's try out an example here. Let's do, actually, why don't you do this? You do bicarbonate, HCO3 minus. So try to remember the rules. Again, the rules, 1, total up the valence electrons. 2, come up with some kind of skeleton structure. 3, complete the octets to the outer electrons, or duet if it's a hydrogen. 4, leftover electrons go on the central atoms. Or, alternatively, if you're short, form multiple bonds to complete the octet. So I want you to find out how many valence electrons you're dealing with total first. Does somebody have it?
You have to have 24 valence electrons?
Yeah, how did you get minus here?
I think the minus, well, I put the minus here.
How did you calculate it? I forgot how to calculate it.
I think it's
All right, everybody should be done with counting up the total number of electrons. We want to count up the total number of electrons because one of the common mistakes with Lewis structures is people put too many electrons or too few electrons because they don't keep track of the total number of electrons. And so you should be done because hydrogen has how many electrons? Valence? 1. Carbon? 4. 3 oxygens. Each oxygen is 6, so that's 18. And then the -1 charge? Add 1. And so that's 22, 23, 24 electrons total. That's all we're allowed.
the carbon goes in the middle.
Yeah, then we got to come up with a structure. And let me give you some hints on structures. 1 hint. Usually you put the least electronegative element in the center. Carbon. And that way all the more electronegative elements can gang up on it. Right? Surround it. Which would be... And so least electronegative goes in the center. Okay. That's hint number 1. Least electronegative goes in the center. Hint number 2. And now, this is what we call an acid anion. Why do we call this an acid anion? Because acid anions have hydrogen written first. Acids have hydrogen usually written first. Not always. Okay, if you have an acid the hydrogen always gets bonded to the least electronegative or the most electronegative element? The most. And so, common mistake with this is people bond the hydrogen to the carbon because they're right next to each other. It just seems logical to do that. But in this case, the hydrogen is not bonded to the carbon.
Is that always the case when there's an acid?
Yes.
So
Whenever you have an acid, you always bond the hydrogen to the most electronegative element. And so let me give you an example of that over here. HClO. What atom am I going to bond the hydrogen to?
The oxygen.
To the oxygen. Why? It's more electronegative, and this is an acid. This is called, you know what this is called? Tell me what this is called. Hypochlorous acid. Good. Good, that's good.
How do you like acid?
Huh? Because once in a while you should go back and review the names, right? Actually, on a weekly basis, you should go back and review the name. Hypochlorous acid. Yeah, it's got to be. Hydrogen bonded to the oxygen. So when we come up with a structure, the structure looks like this, not like this.
Wait, is that an O or a U?
HOCl.
Oh, CL. I thought it was a U.
No, sorry. Cl. HClO? No.
Oxygen.
Right. How about this one? HClO4. Tell me the name of this.
Chloric.
Perchloric acid. Where does the hydrogen bond to?
The oxygen.
To the oxygen, not to the chlorine. This is called hydrogen carbonate or bicarbonate. Where does the hydrogen bond to? To the oxygen. So make sure you do that. And so why don't you come up with a skeleton for this?
So it doesn't zero. Say we want to plus oxygen. So now it's going to be okay, I think I'm done.
What do you mean?
And then the negative is going to go. I forgot how to calculate the negative.
All right, well, we'll continue here. So what was your skeleton that you came up with? Well, the oxygens are going to gang up on the least electronegative. Oxygens are more electronegative, remember? Oxygens are at a 3.5, carbons at a 2.1. What's going to happen to the electron cloud? The oxygens are going to be sucking the electron density away from carbon, basically. Okay, now which of these three oxygens do we put the hydrogen on? Anyone. Does it matter?
Nope.
No, it makes no difference. So which one do you want to put it on? Let's put it on the top one. So far, how many electrons have we used up? 8. 2, 4, 6, 8. And we have extra electrons, so what do we do next? The next step is to complete the octet to the oxygens. Why not complete it to the carbon first? Because oxygen is more electronegative. Oxygen is going to complete its octet before it lets anybody else complete its octet. And so oxygen completes its octets first. So we need how many here? We need 6 more electrons. We just pair them up. So we call that 3 lone pairs, 1 bonding pair. And then how many have we used up? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 22, 24. This is good because do you guys remember how to count octets? How do you count octets? We look at the total number surrounding. So hydrogen has what we call a duet. That's fine because in the first shell, to fill the first shell, we only need 2 electrons. But oxygen's in the second shell. In the second shell, we need 8 electrons. And this oxygen has 8 electrons. But, you know, when we do octets, we always double count. It's the total number surrounding. And so when we look at this carbon, carbon has 6.
Carbon okay with that?
No. Carbon's not okay with 6, is it?
Make a double.
And so if we don't have an octet here, we have to make a double bond. Now we have a choice. We could make a double bond using the electrons from the left or the right. It doesn't matter. Either one is okay. And so if we choose the left one, we have to erase one lone pair to make a double bond. Now when we count carbon, it has 8.
What are the exceptions to those? Like, I know some elements that are okay with having 6. Like, some elements that
Okay.
want octet.
All right, I'll talk about the exception now. Yes, we could use the top one. In fact, let's see what all the possibilities are. So, if I use the bottom left, we get this structure. If I use the bottom right, we get this structure here. We end up with this structure. If I use the top one, we end up with this structure here.
Oh, you can. You cannot do that. It'll violate the oxygen.
So those are just all the different.
These are the three, these are the three possible scenarios for completing carbon's octet. I form a double bond on the bottom left, I form a double bond on the bottom right, or I form a double bond up here.
Yeah, you can.
Would you want us to know, like, do all 3, or just you just pick one?
No, you have to do all of these, because do you know what these are called? These are called resonance structures. They're not isomers because they're the exact same. Why do we care about resonance structures? I'll tell you in a minute. But we need all 3. But one of these doesn't belong.
Yeah, this is the last one.
One of these is different than the other 2. Which one is different? But it looks different, but essentially it's kind of the same. I mean, does everything still have an octet? Yeah. When I look at the octets, this is, oops. Everything has an octet here. Octet here. The octet here is good. The octet here is good. Octet, 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 octet. So when we do Lewis structures, is that all we care about? Is the octet? No. What else do we care about?
Minimal charge.
Formal charge. Did you guys do formal charge in Chem 4?
I don't
Yeah.
remember how to do that.
You don't remember how to do formal charge?
Like, I don't know how to put the negative bicarbonate. No,
All right.
You have to do
Balance
something. You have to
spectrum
count the
minus
number of
minus
bonds and the
zero.
number of
No.
electrons.
No, we're not going to do it that way. Yeah. We're going to do it a different way. How do you do oxidation state? If I wanted to do oxidation state, what's the oxidation state of hydrogen? +1. What's the oxidation state of this oxygen? Remember oxidation state? It's winner takes all. There's no sharing. So hydrogen now lost. So this oxygen, hydrogen is what we call +1. Oxygen is -2. Carbon is, well, here, this oxygen is -2. This oxygen is -2. And that leaves carbon with nothing, which means it's +4. It's lost all its valence electrons. You guys remember oxidation states? Oxidation state is a way of counting electrons where winner takes all. In other words, oxidation state, we assume, in oxidation state we make an assumption. If it's winner takes all, is that more ionic or is that more covalent? More ionic. And in fact, if winner takes all, it's 100% ionic. So oxidation state, we make an assumption. We assume 100% ionic bonds. Is that accurate? No, it's not accurate, but you know, it serves our purpose because the only purpose we have is coming up with some kind of scale or some kind of measuring system where we can compare apples with apples and oranges with oranges. And so that's why we use this. Because if we normalize it so everything's ionic, then we can make a comparison. All right, formal charge. We're going to make the opposite assumption. What is the opposite assumption? Rather than assume it's 100% ionic, we assume 100% covalent. Which means this. Even though oxygen has more pull, we're going to split it down the middle. Oxygen has more pull than carbon, but we're still going to split it down the middle. And so this is what happens when we split it down the middle. One of the electrons in the bond ends up with hydrogen, the other ends up with oxygen. And so now we count the electrons. When we count the electrons, it's like this. Hydrogen has 1, it's supposed to have 1, so it has 0 formal charge. Formal charges we circle. Oxidation states we parentheses. I'll leave it black. Well, oxygen has how many? 1, 2, 3, 4, 5, 6. It's supposed to have 6. It's 0. Carbon, we're going to split it down the middle. So carbon has 1, 2, 3, 4. Because a double bond counts as 2 bonding pairs. And so, yeah, carbon is 0. This oxygen over here.
Wait, carbon has what? 1, 2? What
1, 2, 3, 4.
And why would it be 0?
Why would it be 0? Is because it neither gained nor lost. It broke even.
Valence electron?
Yeah, valence electrons. It broke even with valence electrons. This oxygen over here is not 0, though. What is this oxygen over here? Well, let's count it. 1, 2, 3, 4, 5, 6, 7.
Oh, minus 1.
Minus 1, it came out ahead, 1 electron.
That's what minus 1.
This oxygen over here, 1, 2, 3, 4, 5, 6 is 0. So that broke even.
That's what they mean.
Yeah.
So why would in Chem 4 they make us like count? I remember in Chem 4 they made us count like...
They made you count? Yeah, there's a formula for this. It's, you count the number of lone pairs. It's 2 times the number of lone pairs plus the number of bonding pairs divided by 2. Or it's the number of lone pair electrons plus 1/2 the number of bonding electrons. Or, you know, there are multiple formulas for this.
Is it in the book?
Huh?
Is it in the book?
It's in the book. It's in the book, except that that formula doesn't work all the time.
What?
Wait, so the one you were giving us?
Oh no, that formula does work all the time. Let me take that back. Yeah,
But we can do it that way too, by looking at that.
you could do it that way too. You could do it that way, except you should learn both ways.
Yeah.
In fact, I don't even use the book's way at all.
I think the formula you forget. It's easier to forget the formula.
Okay, so what's the difference? Well, let's take a look at these 2 structures again. And these first 2 structures, there's no difference. They're the same. But the third structure, there is a difference. The third structure has this. Let's look at the formal charges. What's the formal charge on this oxygen here? No,
Plus one.
plus 1.
Yeah, plus 1.
This carbon, 0. This hydrogen, 0. This oxygen, minus 1. We usually don't show 0 formal charges. This oxygen, minus 1. So what is wrong with this structure? What is wrong with this structure is one of the oxygens is a loser, and the other oxygen gain, because one of these has to be negative. So let's say this one stays negative. That means this oxygen took an electron from this oxygen. Think about it, right? Because this one came out ahead 1 electron, this one lost 1 electron. If there's a tug of war between oxygen versus oxygen, who's going to win? No one should win. Does this seem like a stable ground state, or does this seem like an excited state?
Excited.
This is an excited state. You know, it could happen, yes, but not stable. And so this one doesn't belong. The reason why this one doesn't belong is because this is a higher energy excited state, right? This is higher energy compared to these two. And why? It's because of this misallocation of electrons here. And so it turns out we call these, there are 2 resonance forms, not 3, for bicarbonate. And we draw them both. And so the first resonance form, it doesn't matter how you draw it. It looks like this. We sum up all the formal charges to get the net charge. Net charge is equal to the sum of the formal charges. And then we show the 2 resonance forms using this double-headed arrow. The double-headed arrow shows that we had a choice. In the making of that double bond, 2 choices. This is it.
Would it matter? Because like molecules are moving, so it's just that we just split the molecule? Like,
Yes, but the thing is, the molecule's always moving. So notice if you flip this 180 like this, then you end up with the same exact molecule, right? And so this is what you have to do. You have to pin the molecule to the ground, and then see how many ways there are. The problem is that people don't pin the molecule to the ground, and so what they end up with is 10 different resonance forms, because what they end up doing is this. They end up putting the hydrogen like this. They move the hydrogen. This is not right. Do not move the atoms. You have to pin the atoms on the ground and then see how many ways are there to range the electron cloud, the electron density. You do not let the atoms move. Okay? And so fix the atom position. Then determine how many ways to arrange electron density. This is an ad hoc analysis. So what people did was they realized that double bonds are shorter than single bonds. You know, double bonds, you have more electron density between the nuclei. More electron density is going to pull the nuclei closer or push the nuclei farther apart. Yeah, so you got twice as much electron density here, so what it does is it pulls the atoms closer to each other, so double bonds are shorter and stronger, right? Not twice as strong, but stronger. And so what a lot of people think about resonance, have you ever heard the term resonance? Have you seen the Tacoma Narrows Bridge? That's called resonance because the wind frequency or whatever just hit the right frequency for the bridge, and then it started resonating, you know, oscillating with the wind. Well, a lot of people, when they think about resonance, they think of this as being resonating, that is cycling back and forth. And so when they're thinking about resonating, they're thinking short, long, short, long, short, long. They're thinking of these bonds as resonating back and forth because on this structure it's short. On this structure, that same bond is long because we pinned the atoms. Remember, you got to pin the atoms in position. Don't let them move. And so does it cycle? Short, long, short, long. That would be resonating, right? Short, long, cycling, oscillating. Is that what happens? It turns out, no, it's not resonating. You know what's happening? This is ad hoc. What's happening is neither of these structures is accurate, unfortunately. But we use these structures to get more accurate picture. The more accurate is something called the resonance hybrid. You know what a hybrid is? Mixture of the two. And so there's only two, so it's a 50-50 mix. If we have a 50-50 mix, then it's not a double and it's not a single. Do you know what we call it? If it's not a double and it's not a single, we call it halfway between. What's halfway between a double and a single? A 1.5 bond. And so each bond is the same. It's a 1.5 bond. Well, how can you have a 1.5 bond? Okay, and look at what's happening with the charge. Is it going negative? 0. Negative 0. Negative 0. Just cycling. Look at the negative. It's flipping. Here it's negative. Flip. Flip, 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 flip. Is it flipping back and forth? No. Do you know what's happening? What's happening is it's negative 1/2 here and negative 1/2 here. It's evening out. And so how does it do this? Let's talk about that now. There are two lone pairs fixed here and one lone pair that kind of cycles, or not cycles. And so let me tell you how this works. In this sense. How this works is that the electron cloud is not static. What can happen is this pair of electrons can drop into the bond, which pops this pair of electrons out. And this pair of electrons can drop into the bond, which is going to pop these electrons out. And so do you see that by rearranging the electron cloud, by rearranging electron density, we can convert from one structure to the other? Do you see that? And so that means there's a pathway linking these. And what happens is this. Imagine you have a bathtub in this shape. You have a bathtub like this. And you want to put twice as much water on the left side than the right side. And so in other words, we put 2 feet of water on the left side and 1 foot of water on the right side. And over here, we have the same kind of shape here, except in this case, we want 2 feet of water on the right side and 1 foot of water on the left side. Okay, and so is it going to cycle? That is, all of a sudden we have 2 feet over here, and then goes down to 1 foot and 2 foot and 1 foot and 2 foot. Is it cycling back and forth? The water? No. What's the water going to do? The water is going to spread out and form a hybrid of the two. What's a hybrid going to look like? It's going to be 1.5 feet deep. And so this is the whole idea of a resonance hybrid, because there is a mechanism for transferring the electron cloud that is transferring the water. There's no wall here, right? If there were a wall blocking this, the green arrows from happening, then it's not going to happen. But since there's no wall here, the water is going to spread out. And when it spreads out, it's going to fill both sides evenly. And so this is why we have to figure out how many resonance structures, because we got to see how the water is going to spread out, or how the electron density is going to spread out in the structure. And by having the water spread out, or the electron density spread out like this, it tends to stabilize certain things. We'll talk about that later. And so it makes things less reactive, because, for example, if you had a full negative charge here, it wants what? A full negative charge wants positive charge. But if that full negative charge now drops to a negative half, then is it going to be as reactive or more reactive? Maybe less reactive or more reactive? Less reactive. Right?
So which one do we usually do?
We do all of them. We do all of them. All of them meaning we draw out all the resonance structures like this, and then draw the resonance hybrid. So we go till what, 12? 12:30?
Yeah, 5 more.
5 more minutes? Okay, why don't you do this for me then? Why don't you know the structure bicarbonate? Right? We not bicarbonate, carbonate. I drew the structure carbonate. Okay, draw all the resonance forms. Connect all the resonance forms with double-headed arrows. And then hybridize those resonance forms into a resonance hybrid. Do that for me.
Can you explain briefly about the arrow, the green arrow?
The green arrows? The green arrows is just say, take these 2 electrons, pull them off the oxygen, and stick them into the bond.
How do you know which way it goes to? From where to?
If we took these electrons off here, we'd make a triple bond. And then if we took these electrons away from here, we'd have no bond. And so there's only one way to go.
I mean, like from the double bond, it goes to like the oxygen side. From the electron goes to the bond.
Well, try it. Try it.
What do you mean by
How do you know you don't? You just try different ways. Try it. You try different ways and then figure out which one is the most.
So you're saying that green arrow means like the electron transfer?
Right. The movement of electron density. Try it. So, for example, I could just do this. But is that going to make anything stable? No. So we try different things and see how things can rearrange. That's it. How do I know? I didn't. I just tried it. And I tried all the scenarios.
Okay.
Like, you know where the
I was just asking so
Yeah, I'll do it right now.
grading at some point and then putting the grade book online at some point.
Yeah, you could take this right after I'm done checking it.
Okay.
I'm so tired and I'm hungry. I don't know. You might have stuff Can we do it for homework?
Hmm?
Can we do it for homework?
Yeah. All right. Well,
I'm so excited.
Calm.
That